Okay, and we are officially recording. So again, what I'm going to do today is walk through so we're going to talk about, let me give this a go. Let me just try it really quickly.
Wow. Can you do it with a pencil marker?
This is really awful since I don't have a very good, so I can write on this. All right.
You haven't put up the recordings yet, though, right?
Nope.
Yeah. Okay. Yeah.
Nope.
Yeah.
All right, that's actually probably, I'll start these tonight when I go back, and this will be the first one I go through. So this is the info for the path analysis. And yesterday we focused on confirmatory factor analysis with an emphasis on the notation for the diagrams and the equations, and then consequently the from the equations into the matrix notation. I'm going to put that aside for a bit, and we will come back to that. And surprisingly, what we're going to do is we're going to talk about path models, but then I'm going to probably use a confirmatory model to actually demonstrate some of the things that we're going to talk about here. It works a little better. Okay, so with path analysis, the first thing to recognize is this is something that's been around for quite some time. I think one of the earliest papers that demonstrated it was probably, I think, in the 30s or 40s. It is a technique that is, if you have the ability to calculate the multiple regressions, you can actually write out the mathematics for this without too much difficulty if you could get the computer to do the multiple regressions for you. The path analysis was the first step towards this idea of developing a causal model. That's where you want to set up a situation where A influences B, B in turn influences C, C influences D, and you've got this chain of causal influence happening. The philosophical concern to keep in mind is that lack of fit is proof that your model doesn't work. But again, we know all models are wrong, so that doesn't really help us. Lack of non-fit, meaning it seems like it might fit, is suggestive that it might be correct. So correlation doesn't prove causation, but causal models can indeed be supported by observed correlation. So that's kind of the little caveat I'll throw there. And the one thing that is always emphasized is that the more you can respect the temporal ordering of events, the better off you are for having a model that could at least stand in as a causal model, something that might explain something. So ideally, A should be measured before B. When that's not possible, you want to attempt to justify that what created A is something that happened before you created B. So it's very common to see this. This is in when you're collecting survey data to not have that.
I guess my question is, so what if you collect A, B, C, D at time 1, and then you collect A, B, C, D at time 2 and time 3? Mm-hmm. Can you then do a model between A at time 1 and B at time 2, even though B was also collected at time 1?
Sure. Yeah, you can. So when you have, so the question is whether or not if you've collected the same set of data across time, which ones can you then have influence in the others?
Yeah.
That's totally fine. Yeah, to say that what happened at A's version of time 1 probably is influencing A at time 2, but then it's more likely that if there's a connection to B, it's better to look at it from A at time 1 to B at time 2.
Okay, and you just like control for the other.
Yeah.
Mm-hmm. And also you can see the change of the relationship between A and B across time.
Yes. So to look at the change across relationship, you would essentially you could essentially just have A influencing A for all of them, or some common thing that's influencing A through E, A, B, C, D, E, at time 1, and that's where you'd sort of have the factor model, and the factors would be affecting each other at time. And I'll probably try to draw a picture like that as well, so we can kind of see one of those. Mm-hmm. Okay, so again, all models are wrong. A model should be So if we know that they're all wrong, what do we do? Well, a model should be plausible to experts. The results should be reasonable for both the context and what we know already. So, for example, existing literature and other empirical research that's been collected. The model should be useful for prediction purposes. Now, this means this is indeed intended in the common parlance of prediction, meaning the psychic is going to predict what happens tomorrow type of prediction. Statistical prediction is when you can say, I can predict how much variation is going to be determined by one variable to another. Well, that's happening as well, but in this case, a model is intended for predictive purposes. And the general rule of thumb is that parsimony is valued over complexity. The easier and more basic your model, the better it is, though complexity has its benefits, and there are times when that needs to be acknowledged. When we say something along the line, let me think of a really good example that changes. Example is not coming to I'm moderating the example is not coming to my mind really quickly. So when we want to say that one thing influences another, the fewer things that we can say are influencing our outcome, the better. So if I want to predict, what's something we could predict? My brain is just really just like scraping the bottom today. Academic achievement.
Sure.
We all care about academic achievement. We predict academic achievement, and we want to say that SES is related to academic achievement. There we go. So SES is related to academic achievement. And we make that prediction, and if we can just say it's SES, that's a very simple model. And even if we know that we're going to be wrong, if we accounted for a fair amount of the variance, that's a really good thing. But maybe it's the case that there's something else with SES. So maybe it's not just SES, but maybe it's both SES and there's something different for people whose parents went to college versus people whose parents didn't go to college. Then we see that, well, look, SES does influence academic achievement but what we see is it's much weaker for parents that went to college than it is for students that parents didn't go to college and are coming from poor and lower SES environments. So that one variable is now breaking apart additional information to show that it explains the nuances of the situation better. So in that case, we do want a more complex model. It's giving us more information. So that's where you then have to decide easier models or more complex models. Which way do we want to go? Okay. So path analysis versus ordinary least squares regression. Path analysis is better in that it's better than multiple regression analysis because it avoids multiple tests, because technically with ordinary least squares regression, you have to conduct multiple regressions again and again for all the variables you're looking at. And the other problem is that it also doesn't, in and of itself, account for issues of multicollinearity that might exist. Now that said, both of those first two dashes are technically not fixed when we do path analysis in the quote-unquote old-fashioned way. The structural equation modeling techniques that are available are actually, they can do these things better, but what I'm about to show you doesn't actually meet that criteria because it still does actually just that. It runs a whole bunch of multiple regression equations and puts them together. Now, regardless of that, once you have your solution, it does allow for the analysis of both direct and indirect effects, which is something that ordinary least squares on its own can't account for. So just to clarify, direct versus, actually the next slide is the best one to look at. So this is, I want to give a very straightforward example here. So the diagram and the equations, when we talk about path analysis, where the term structural equation modeling comes from is actually from the path analysis vocabulary. Path analysis introduced the idea of the quote-unquote structural equation. In the diagram, A influences B, A influences C, and B also influences C. So what we see is that this was a classic full mediation model. The idea is that the equations should capture the structure of the graphical model. And what we're seeing now, let me explain why I chose to write the notation this way. generally speaking, when you do path analysis, you almost always use the standardized regression coefficients, regression equations. And so that's why I have the instead of variable B influencing C and Z and A influencing C, it's actually the standardized value for A. So this is just A and turning them all into Z scores. So this is convenient because, one, I don't need an intercept because the average is 0 for both of the variables, so the predicted value will be 0. Thus the intercept is 0. And then technically this standardized coefficient here is for A predicting B. That's just the correlation between A and B. That's all that is. In this case, there are technically multiple. These are partial slopes, but still standardized values. So the path analysis is taking this structure that we see here and converting this to an equation. So what we actually have is this would give us an equation for B because A predicts B, and in turn it would give us an equation for C because A predicts C and B predicts C. So we have in the actual equation representing this a coefficient times the variable for A equals the variable for B. I just realized this looks like a minus sign. That's actually not a minus sign there. Bad notation on my part. And then the coefficient for A times the variable for A plus the coefficient of B times the variable for B will predict C. So these are the equations that describe the structure for the model. So that's where the term structural equation comes from. And in this case, again, we do have a mediating model where A has a direct effect. This is, I'm going back to this slide just for a second. So the nice thing about path analysis is that it lets us assess both direct and indirect effects. So in this very simple mediating model that we have here, A influences C directly as it's been drawn, but A also may have an effect on C by the effect it has by first influencing B, which in turn influences C. Now, in this equation, what we're going to see, the direct effect for A is simply the direct effect for A on C, the direct effect for A on C is just the coefficient, in this case beta sub CA. That's the direct effect. The indirect effect would be what is obtained by this path followed by this path. And here the coefficient is beta sub BA. Here the coefficient is beta sub CB. The indirect effect is essentially just those values multiplied together. Now, I'll come back to that and reiterate that when we talk about the rules for the paths.
I also heard the word total effect. Is that something similar as indirect effect, but it's like larger model?
Nope, but it's not an issue of the larger model. It's just putting those two together.
Oh, okay.
So the total effect is when you take both the indirect and the direct effects. Now there's two other effects that we'll talk about, and those are not included when we talk about total effects that are reported in the literature, but they are important when we're actually constructing our models. Okay. All right, so let's take a look, and what we need to do is a little bit of quote unquote variable classification. So I need to introduce a new set of terms, and these vocabulary terms are going to prove to be important for us.